Yeah, I'm Sean Mcilvane from the University of Georgia, and I'll be highlighting my poster on X-ray emission from charge exchange with iron ions. So first, the motivation for this is that first off, X-ray emission from charge exchange has been observed in extrasolar regions, and we're focusing on the spectrum observed in the Cygnus loop, which we suspect is due to the charge exchange with iron 16 and iron 17 ions around zero point 0.7 keV. And this charge exchange data is needed to fully model the X-ray spectra observed, and it'll be used for future and present X-ray emissions, including Hitomi, Chrism, and Athena. So for our methodology, we use the multi-channel Landau-Zener approach to calculate cross sections, and we use multiple code packages to do our calculations. So first, we use AutoStructure, made by Mullen et al. AutoStructure, we input the energy levels provided by NIST, and it solves the time-dependent Schrodinger equation to calculate the theoretical energy levels for all possible states, and then also calculates transition probabilities and transition energies. Then we go to Stilkelberg, which automates the multi-channel Landau-Zener calculations and generates, total N-resolved and NLS resolved cross sections using the energy levels. And then for Kronos, we input the cross sections, the transition probabilities and transition energies to generate X-ray spectra using a cascade approach. And basically, we track, when charge exchange happens, electron gets excited, and it doesn't, immediately go down to the ground state. It might decay to, 3 different states before going to the ground state. So it kind of cascades down. And so we use Kronos to kind of track that using the transition probabilities and transition energies. Now for our results, figure 1 shows the N-resolved cross-section for iron 17 helium. We declare N equals 8 as the dominant N level because it has the biggest contribution to the cross section at 1 keV, and we'll be using that in our following figures. So figure 2 shows the NL resolved cross sections for iron 17 and helium at the dominant N level 8 at various energies. It's hard to see because it is like a small, but at 10 eV, the peak of the cross sections seem to be around L equals 3.5, whereas at 1000 eV, L for singlets and triplets peak at L equals 2, which correspond to the D states. You'll also notice that the triplets and singlets are separated proportionally, and you'll see that in each of these figures, the singlets seem to contribute more to the overall cross section than the triplet states do. And for like L distributions and basically what we did was we summed up all the states as certain L. So like 8D, we summed up all the states at 8D for L equals 2. Now we go to figure 3. This would be the comparison of L distributions for iron 17 and helium at N equals 8 and 1 keV. Basically, we're comparing our multi-channel Landau-Zener method L distribution toward previous analytical L distributions. And then we're going to go to figure 4, which is a comparison of L distributions to iron 17, all of our neutral targets. Since we did do like iron 16 all the way to iron 24, and we did targets including helium, hydrogen, H2, water, CO, CO2, and N2. This is just comparing the collisions of iron 17 with different targets. And you'll see that most targets peak at L equals 4, which correspond to the G states.
All right, 1 more minute, just to let you know.
Okay, thank you. And then figure 5 does comparison of L distribution with iron ions and helium at N equals 8 and 1 keV. Typically, the higher charged irons have a higher peak at higher L's. And then we'll go on to our spectra. I would have put more spectra if I had a little bit more space, but basically this is a spectrum of iron 17 colliding with helium. and the red represents our data, or like my data from Charge Exchange and using the multi-channel Landau-Zener method. And the blue represents emission due to electron impact that we found on NIST, Atomic Spectra Database. So basically what we're going to do with this data is that we're going to compare this data to what's they're observing in Clemson. Clemson's observing or making X-ray spectra measurements, and we're going to compare it to this data to their data to benchmark our current calculations.